Először azért magyarul mondom, hogy a következő és ebben az első tudományos ülésen az utolsó előadás, ahogy a bevezetőben említettem, szemléltetni fogja, hogy az a tudomány, amit itt láttunk, ami sok esetben látványos, amit Henning professzor mutatott képekbe, más esetekben megmutatja azt a matematikai hátteret, ami az elmélethez kell, hogy miképpen lehet a művészetet és ezt a tudományos eredményeket összehozni. Jól mondom? Jól mondom. Well, as I told before, we will see performance. Performance is okay. It's correct. It's correct. How can the science, the very, very serious science, grow into the music and into the life for us? Okay, Professor, please.
Thank you.
Stage is open for you.
So, ladies and gentlemen, first I should turn the topic from the exoplanets to stars and music. So first I invite you to some kind of audio-visionary travel to the stars. Something is not... so for this transition from exoplanets to stars and music, the Kourou satellite helped us, because this satellite, as its acronyms tells us, rotation, convection, rotation, and transits, observe the stars, and from the light variation, it can find pulsating stars, and from the stellar pulsation, we can predict the rotation of the stars, the convection inside the stars, and from this kind of transits of planets, we can discover new exoplanets from the light variations of these distant stars. So, to go, to the music of the spheres, I have to go back to the ancient cultures. In ancient cultures, astronomy, mathematics, and music was very close to each other. Actually, these were exactly the same principles in the ancient cultures. The nice example from the Greeks, the Pythagorean approach, they found the relation between mathematics and music just by studying the strings and the ratios of the frequencies of the strings and the geometry of the strings. And from the knowledge of the Greeks on the planetary motions, the spheres with planets on, they predicted some kind of music of the spheres. Later on, when Kepler found the real geometry of planetary motions, he introduced a new way of music from the planets. That is for Mercury, and the scale is from the velocity changes during the planetary motion. Later on, there were lots of musicians who used the stars, the imagination of stars, to compose some music. One of the most famous examples, Horst, he composed the planets. I just can show you some very short. So that was the musical theme by Horst for Venus, and the same for Mars. And later on, by the help of radio telescopes and modern techniques, there were new challenges for the combination of music and astronomy. An Italian lady, astronomer and musician, Fiorella Terenzi, composed some music by the radio signals of radio telescopes in electronic music studio, and she produced music like this one here. And later she started to sing also. It is kind of okay. So there are lots of possibilities to combine science and music, even in biology and chemistry. There is a nice cooperation between an American biologist and a musician, and they used the structure of DNA to make the scale of music. And it turned out that the structure of DNA can produce some real musical structures, just some minimal touch of the system. And there are lots of other things, like crystals or brain waves. I just show you the brain waves. That that is a nice introduction with some brain and electronic instruments through an electrocardiograph signal. So there are, again, lots of possibilities. And if we are looking through the nature, we can find lots of nice sounds. I have a short quiz just with some of my sounds from my collection. I wonder how many of those you can find out. This one is the simplest one. What do you think about this one? And this? Simple one too. And it is not the steam engine, but something else. Okay. And my favorite one. So let's see the solutions of this quiz. So the first one was a slow pulsar. We can compare with the crab pulsar. It's a faster one. There were some animals like this blue whale and the echolocation of a bat. The scale is changed. The bat was slowed down to be audible for human ears. The blue whale was speed up to turn the sounds to the audible region. And for the last one, I just made a scale change by 3 octaves deeper, and if you listen to the real one, then you can recognize the sound of the bird. So just by changing the scales, we can hear lots of sounds from the nature that we cannot hear with our ears. So that opens some new possibilities for making music or making sounds from stars, for example. For our approach to the music of the stars, compared to the Pythagorean approach, was to use the real physics of the stars and use the connections between the acoustics of the stars and the acoustics of the real musical instruments to find some kind of virtual musical instruments. And we also used the physics and the temporal variations of stars to get some kind of structure inside music. So to introduce these similarities between musical instruments and stars, I just show some picture of stellar pulsations. It's a hydrodynamical model of a pulsating stars. And actually these oscillations inside the stars are from audio waves moving inside a star. So to get some information of these sounds inside the stars, we just have to observe the stars, check the variation of the light in time, and from the variation of the light we can tell what kind of sounds are inside the stars. Of course, we can use lots of knowledge of the physics of the stars from different diagrams. We can use the structure of the stars to get the models of these sounds inside. And of course, we should put all these stellar sounds inside a wide scale. Up to my knowledge, the deepest and the highest pitches in the nature are, the deepest is some kind of waves around the supermassive black hole, and the highest tune is a nano guitar. Some funny American physicists made this structure like the microchips in computers from silicon, and they were able to make some sound of this guitar by a photon impulse hitting the string. And the difference in frequencies between these two structures is 75 octaves. I use the frequency difference in musical notation in octaves. The audible range is 10 octaves wide in this blue box. We can see here this point, the nano guitar, here these waves around the supermassive black holes, and the sounds inside the stars are in this 20 octaves wide yellow box. So that's the structure of the sounds in the universe. If I put it in a different figure with lengths of the object or the linear scale of the objects in kilometers and the frequency again in octaves, and I use the normal A for the 0 point, then we can see the organ pipes here where there is a clear relation between the frequency and the length of the pipe, of course, and all the other objects is very close to this linear relation. You can find here the pulsating stars, the sun, the earthquakes, and white dwarfs. So all the objects in the nature can make some kind of vibrations, and there is a very close relation between the frequency of these vibrations and the scale size of these objects. Of course, there are lots of other possible sounds in the past of the universe, but I have to skip because we are in great delay in the program. So to understand the connection between musical instruments and acoustic instruments, first we have to understand the stellar pulsation. Actually, you don't have to understand these equations here. These are just the simplified equation of stellar pulsation in a limited case. But the nice nature of this equation that we can simplify it just by introducing new variables, and then we have some equation which is very similar to the Schrödinger equation. And if we find some more parallel between these equations, from Schrödinger equation we can go to the Bernoulli-Webster equation, which gives the relation between the cross-section of a wind instrument like a trumpet and the possible sounds of these wind instruments. So from these parallels between pulsation and equations and wind instrument, we can have this nice figure. From the structure of a star, we can design a trumpet which has the same frequencies as a star we used for the design of this trumpet. Unfortunately, these musicians, after my talk, cannot play this wind instrument because we don't have a real instrument like this, but fortunately, to the computer techniques, we can construct some virtual musical instruments for this trumpet and for the other stars. Just some nice structure of this trumpet is this narrow part. That is unusual for real trumpets to have this narrowing part, but it has a very important feature in stellar structure. That is the potential we used in this Schrödinger-like equation, and it's from the structure of a Cepheid star. It's some scale height in sound days, the travel time of sounds into the stars, and there is a very large structure here. Even if I change the scales, it looks like a delta function. So the structure is very close to a very simple model, just some flat potential function with one direct delta function. And if we check the sounds from these very simple models, then we have these very strange frequency ratios versus the location of this delta function. What this figure tells us for the difference between the stars and the musical instruments, for organ pipes and strings, the period ratios or the frequency ratios are integer ratios. So there are natural harmonic sounds in musical instruments. But if we go to stars, or even this very simple toy model of stars, then we have very different frequency ratios and even such kind of avoided crossing that we can expect for quantum mechanics, for example. So what are the ratios of these frequencies? Just to show a few of them. That's the deepest, the fundamental mode. If speed up to the audible range, then in comparison, the next sound, the first overtone is here. You can hear that it's not a real musical ratio, at least not for the classical music or the classical rock music. But even with these sound sequences, it is possible to make some kind of music. It's a figure just to demonstrate the differences between the harmonic sounds of the musical instruments and the sounds of the stars. I should skip. We can compare these oscillations even with soap bubbles. I don't show here the real soap bubbles because outside the people cannot feel the real structure of this bubble. But like the stars, the bubbles are spherical structures, and there are lots of similarities, at least in the mathematical level, between the stars and soap bubbles. And if we are searching for frequencies of the stars, then we have to find very similar eigenmodes of the objects. I just show you some of these oscillations, and stars can make very similar oscillations. And if a bubble can have such a deep variety of oscillations, the stars should have the same very wide variety of oscillations. Another nice feature of the stars, that some of the stars likes to pulsate and the others do not. So what could happen if a huge musician could kick a star which does not like to pulsate? Then, like the piano, when the hammer kicks the strings, it makes some sound. And it happens to the star that after some time, the oscillations decay. And there is a nice structure inside the sound, because if this narrow part of this trumpet, some of the overtones takes a longer time to decay, and it makes a constantly changing color of the sound. I hope you can feel the changes in the sound even outside. And if you go through a region of the stars with different temperatures, like in this figure, we are going to higher temperatures, then are different decay rates of the sounds. The decay rate increases. These three guys like to pulsate. These two pulsates in the fundamental mode, and you will feel the difference when it turns to the first overtone. It goes to a higher pitch. Now we're leaving the stars which like to pulsate, and the decay is very fast. Of course, if we observe a globular cluster, we can see almost hundreds of stars. You can see the stars here pulsating. It's a single image taken at our Piszkéstető mountain station, and I used the data of the guys who observed all these RR Lyrae type stars inside, and I made this animation by the real variations of the light, like a time-lapse animation. And at the same time, I speed up the sounds even higher level to make this kind of noise of all the stars inside this globular cluster. So go to other kind of stars. These soap bubble-like oscillations can tell even that the star is inside a binary system, and if we speed up the variation, the real observations of one of these kind of stars, then you can hear this kind of strange harmony from these dozen frequencies of the same star. Of course, our sun vibrates. Fortunately, the amplitude is small, so our weather does not change due to these vibrations. It's a really nice and interesting sound. Actually, these are just sub-samples of the sounds of our sun. Okay, let's go to the next animal from this stellar zoo. This star has some magnetic field, and due to the magnetic field, close frequencies can be observed, and these close frequencies makes this beating, this amplitude modulation. Actually, this sound can be used even for classical music. And there are very complex sounds, like this one here from R. Scuti. This figure very similar to some kind of musical note. The vertical axis is the time in days, the horizontal axis is the time, and the vertical axis is the frequency. But the interesting point is the sound of the stars, and we found that the star has some chaotic variation, so it is some kind of special noise. And there is one more connection from the analysis of the stars and music. Some people at the Institute of Musicology at Budapest used our code to check some of the old folk song recordings by Bartók and Kodály, like this one here. That's the same structure that I showed for the light variation of R. Scuti. So the methods are same for analyzing music and analyzing the stars, and this cooperation made it possible for me to meet a very nice composer, Kolláth Zoltán, who helped me a lot to compose music. Actually, he composed lots of music for the stars. So before one of the compositions I would like to show you, I would like to introduce the orchestra of this music. The orchestra is from these stars, like very simple variations of Ara Lyrae stars with different kind of complexity. Now we can hear two different frequencies. In some of these stars, the Blaschko Ara Lyrae stars, there are some nice modulation. Okay, and we already heard this sound of Theta Tucani from this binary star, and also these magnetic stars with this nice modulation in amplitude. Another one with a different scale in modulation. Solar oscillations, R. Scuti. Of course, you can use this kind of instrument even to play one of the planetary scale by Kepler. This one is Mars. And then here are the music. Actually, I'm in time. So this was the first composition Jenő Kyler made for the stars. And just for some musicology point of view, it has a global form very similar to the traditional folk songs in Hungary. Some A theme with its variation, two different themes, and another variation of the first theme. And the structure of the first two themes came from the frequency ratios of these different frequency ratios inside the stars. So not only the sounds of this music, but the structure of the music is motivated by stellar physics. So again, the orchestra we used actually for these instruments with different kind of colors, besides of the real observed stars, we use lots of models of stars. These are the strange Cepheid sequences with these avoided crossings in the frequencies. We use these stars hidden by this huge virtual musician, these stellar bells, and all the other stars I have already introduced. And again, this is the score of the music with some samples of the sounds like the sun here, this is the Ars Scuti, and actually this one here is familiar from the previous sounds. This one is a new star, GD358, just the phone number for this star, and the composer used these bell-like sounds, some kind of nice structure in the music, and he introduced some kind of combination of different stars. This decaying sound can be mixed with another star, and he used all the partial sounds of this decaying stuff here with another star, and then it turns to a very nice sound itself. So after the parts of the music, this is the whole score of this first composition for stars, and please listen to this 5 minutes of stellar music number 1 by Jenő Kajler and myself as the maker of the musical instruments and some ideas for the music. So thank you for your attention, and you can find this music with better sound quality on the internet on these pages.
Thank you very much, Professor Kolláth. It was a very clear demonstration that we have to learn a lot from the star, and we can put in our Earth life very, very much from this sphere. If anybody has a question from the remote station also not, then thanks again.
Thank you.
Ich werde es auf Ungarisch weiter sagen oder in English. Thank you very much for the auditorium here, and after this scientific session we will open the new study. Az első tudományos ülés után, mert miért ne állítsuk fejre a világot, mert teljesen mindegy, hogy most a Föld melyik részén állunk, alul-e vagy fölül. Tehát az első sikeres előadássorozat után, most rövid technikai szünet után megnyitjuk az új stúdiót, és bemutatjuk önöknek, hogy valójában itt belül milyen a világ. Egy kis technikai szünet, és folytatjuk. Köszönöm szépen. Thank you. Jó volt.